So let's see if I can move this out of the way. All right, cool. So thanks, Mark, and others for inviting me to talk. I'm just going to talk a little bit about some of the research that we're doing in the Center for HCI at Virginia Tech. Specifically, the topic that I chose for today is about content creation in outdoor augmented reality and some work that we've been doing in that direction. Before I get started, I'll give one apology and then a little bit of background on myself. So the apology is that after the talk is over, and if we have any Q&A, I will be leaving the call a little bit early today, so I'll probably need to leave around 12:40 or so. But I'm happy to follow up with anyone afterwards. Background, I've been at Virginia Tech for about 20 years. My individual group is the 3D interaction group, and we've mostly worked on interaction techniques and user interfaces for VR. In recent years, we've been shifting more over to AR. I'm part of this larger group called the Center for HCI. I'm actually the director of that center. It's about 45 faculty members from all over the university who are interested in the interplay between people and interactive computer systems. And one of our big kind of thrust areas is in what we call immersive experiences, which is VR, AR, and visualization. So that's where I come from. So let's see here. There we go. So I want to motivate this work with this kind of image and idea. This is not an image from our work. It's just from Google Images. But the idea is, what if we could design new buildings using outdoor augmented reality? So not just building models on the computer, not just building scale models physically, but going to the place where the building is going to be located and placing the building design and editing or even creating the building design from scratch so that you can see it in situ in its location. So that's an easy idea to understand, but it actually turns out in practice, of course, to be really hard. So the things that we need to be able to do to achieve this vision, first of all, we need to be able to use AR outdoors. And in that image, it was an iPad, right, looking through a handheld screen, which is easier to use outdoors. I'd like to be able to do it with head-worn AR. I'd like to be able to do it in a large area where I can walk around and see the proposed building or whatever it is from any point of view in the area. And I'd like the AR user not just to be able to visualize the structure, but also to be able to create new content and to do that precisely. And so that could be designing a new building, as I said. That's kind of maybe the most difficult of these examples, but it could also just be placing annotations at locations in the real world or developing an AR tour of an outdoor area. So that's kind of where we want to get. There's a number of challenges, obviously, in getting to that point. So we're all aware of the technological challenges. The most important one from my point of view in this talk is that we don't always have, in fact, we often don't have a detailed model of the environment, the geometry of the large outdoor area. We might have a little bit of information from something like Google Earth or other models that have been built, but those are not going to capture all the details, and they're certainly not going to capture the dynamic aspects of the environment, like people and cars and new foliage and all sorts of things are not going to be part of the model. So we really need to be able to do this in a way that's model free, where we don't assume the existence of any model of the environment. Of course, there are also issues like insufficient display brightness if you're talking about an optical see-through headset for AR like the HoloLens, and lack of precise or accurate tracking in large outdoor areas. And we're not really addressing either of those in this work, but I thought I'd mention them anyway. There's also, besides technological challenges, there's human factors challenges, right? So a very important one is that people's ability to perceive depth and distance is limited. We don't have great distance perception, even in the real world at large distances. But in a model-free AR setting, we lose kind of the most important cue for object depth, which is occlusion. So if there's no model, then the augmentation is always going to appear on top of the real world, right? So that means that occlusion cues are going to be misleading, and it's going to be really hard to understand what you're seeing. Secondly, there are kind of motor control issues. So people have a natural tremor in their head and in their hand. And so if we're using head pose or hand pose as a way to give spatial input to the system, then we have to be able to mitigate the effects of tremor. So we started out this work by addressing the problem of model-free point marking. So if I'm gonna be able to create any content in model-free AR, I have to be able to specify 3D points in the environment. And so how do I do that without a geometric model of the environment? And once I've figured out various techniques for doing that, I'd like to be able to compare them and look at accuracy and precision and speed and overall user experience. So we started with two kind of basic ideas, which are pretty obvious if you think about this for more than 5 minutes or so. So one way that we could do point marking without a model is a perceptual technique. So as shown on the left here, the user can look at the target, which in this case is the tip of this lamppost, and that creates a ray going from the user position towards the target and beyond it. And then once we've got the ray, we have to specify the distance, right? So how far away is the target along this ray? And so you could do that, for example, by sliding interactively a box or some other virtual object along the ray until perceptually it appears to be at the target location. So that's one way we could try to do it. A second way we could try to do it doesn't rely on human perception. So this is kind of a geometric triangulation technique. So the user looks at the target from one location, and that creates one three-dimensional ray. They walk somewhere else, and they look at the target again from that location, which creates another three-dimensional ray, and we intersect those rays to determine where the target position is. So those are kind of the basic ideas. And we did an early study where we kind of compared these ideas outdoors using the HoloLens. It was really difficult actually to use the HoloLens outdoors for this study. And so you see some of the caveats there. We only ran the study on cloudy days so that we could actually see the display. We did it where the user was standing under the shade of a tree to help with brightness, but also to keep the HoloLens from overheating, which it does pretty easily. We had the user only walk on a very short baseline, so the two locations where they created their rays were pretty close together, maybe about 10 feet apart, and that kept our tracking fairly accurate. And then we tried to improve the tracking by adding in, we placed a tripod in the environment so that the HoloLens would have something to track on. Most of the environment is too far away for the HoloLens to track on, so we added this real object. Anyway, so we did the study. We had people mark these lampposts that ranged between about 15 and 85 meters away with the perceptual and the geometric technique, and here are the results. So perfect performance is along this dotted line through the center of this graph, and you can see that the perceptual technique is pretty bad, as you might expect, because our depth perception, our distance perception is not that great, especially in the absence of occlusion. So it gets bad pretty quickly as you go out beyond about 25 meters. The geometric technique is pretty good, again, as you might expect. There's some inaccuracy there at greater distances beyond 50 meters or so. We think that that's mostly because of tracking inaccuracies, though, and not because of problems with the technique. So the geometric technique is definitely more accurate. It also turns out that it's less precise. So you see that it's got a bigger variance than the perceptual technique at those large distances. And that's mostly due to head tremor. So we're having people point at these targets with their head. They're positioning a crosshair over the target with their head. And head tremor causes them not to be able to do that very accurately for any given ray. And so you may or may not have the crosshair over the target when you press the button. So we figured out that we need then techniques that mitigate this imprecision of head-based pointing so we can do it right every time. So we came up with two techniques to do that. One technique basically just uses more rays. So instead of one ray from each location, we shoot lots of rays from each location. So we kind of look at the target over a period of time and gather a bunch of rays. And then by intersecting the two sets of rays and taking some sort of weighted average of all those intersections, you can figure out a pretty good estimate of where the user was actually trying to target. So we call that VectorCloud. The second technique is image refinement, and here we still only shoot one ray from each location, but we let the user refine the direction of that ray by taking an image with a HoloLens camera and then moving a cursor over that image to more precisely specify where the target exists in the image. So I hope that you can see these videos. They're not supposed to have sound, but let's see if I can turn that off. I hope that the conferencing software lets you see the video, but basically what we're seeing here is somebody using VectorCloud. So they are looking at the target from one location, they shoot a bunch of rays while they hold down the button. They move to another location and shoot more rays at the target. And in fact, in this example, I think they're going to move to a third location. Let me fast forward a little bit here. So they move to a third location and shoot rays, and the intersections of all those rays end up giving us a target location, and now just walking towards the target to show you that it's actually pretty accurate. So that's the multi-sampling VectorCloud technique. The image refinement technique looks more like this. So again, you kind of look at the target and you get an image taken by the HoloLens camera, and you can actually zoom and pan that image as well, and then place this cursor very precisely over the target location. And then we still have to triangulate, so we do it from another position. This time the image was not even, the target didn't even appear in the zoomed in image, so we have to pan until we can see the target location. And again, precisely place that ray, and then the annotation gets created. And we've marked a point with pretty high accuracy based on that technique. Okay, so we did two experiments to look at how well these techniques perform. And we actually did both of these experiments in what we call AR simulation. And what that means is we did the experiments in VR, not in AR. And that's just to avoid tracking issues and brightness issues and overheating and all that kind of practical stuff that happens when you use the HoloLens outdoors. So this was a VR simulation of AR. But it's important to say that we did not use occlusion cues. So the stuff that was virtual in these simulated AR interfaces always appeared on top of the stuff that was kind of the real world in the virtual environment. So what we see from this first experiment is VectorCloud versus the baseline geometric technique. We found that VectorCloud did what it was supposed to do. It significantly improved precision. So the variance at each distance is quite small compared to the variance that you get with the geometric technique. So that was great. In the second experiment, we wanted to compare the image refinement technique to VectorCloud to see if image refinement could be even better. And here's some basic results here. That this is a slightly different format of the results, but the image refinement technique with zoom, the one that I showed you in the video, is the red bar in these things. And you can see that even at a distance of 85 meters, the average error was very close to zero and the variance was quite small. So this image refinement technique is really quite good. It was more accurate, more precise, and it was preferred by the participants in the study. Now, I should say that the image refinement technique relies on the fact that you have a good camera and good tracking. And the HoloLens camera is not that good. As you saw in the video, it's really blurry when you zoom in on it. It was more kind of idealized in this study. We were using kind of an idealized virtual camera, so we wouldn't get exactly this quality of results with the HoloLens, and we tried that. But image refinement was still better even with the actual HoloLens used outdoors. Okay, so now let me go back to kind of my motivation. I want to use these point marking techniques as the basis for doing something like building design, like creating content in outdoor AR. And so we've actually done that, and we built an application that is based on these marking techniques that I showed you. In fact, in the application, we use the VectorCloud technique that allows you to mark points on real objects like existing buildings or roadways or sidewalks or whatever in the real world, and then use those as references to help you construct a proposed new building. And the first thing I wanted to say is that we first prototyped this in VR again, so it's kind of a theme here. So to avoid all the practical issues of, how can we do this in AR with current technology, we prototyped it in VR just to see how it should work and what should the interface look like and so on. And so that's what these screenshots are of. But then we went ahead and we did implement this in the HoloLens. And so I'm going to try to play these two videos simultaneously, which is not always the easiest thing to do. And what you see here is kind of a first-person view through the HoloLens, and then a third-person view from another HoloLens, actually, that's capturing this. And so the way this application works is you mark real-world points using the VectorCloud technique. And you can see the user has just marked a couple of real-world points and created a reference line based on those. So that reference line tells you, here's some geometric information from the real world that is going to be useful in constructing the building that we want to make, the new building that we want to create. A couple of notes here as he continues to work. First of all, you can see that this is done indoors, and so again, that was just to avoid some current limitations of the HoloLens, but in a large indoor space that's kind of like being outdoors. Second of all, you can see that he's only walking back and forth between two kind of fixed points in the real world that are marked with these white columns. And that's to avoid tracking inaccuracy with the HoloLens. So we always know exactly where the user is standing. So it's more of kind of an ideal AR situation. And thirdly, you'll note that this the interface is in Portuguese here. I don't know if any of you read Portuguese, but this was a student of mine who was from Brazil, and he did the work here at Virginia Tech and then went back to Brazil and ran the study there. So anyway, what he's been doing is creating these reference lines, and now he has moved one of the reference lines to align with another feature in the environment, this column kind of down at the end of the space, and he's then cloned that to make two parallel lines. Now, using intersections of all those lines, he's created a rectangle, and he's going to split that rectangle into two parts. This is going to be the footprint of his proposed building. And then finally, he's going to extrude the two kind of sub-rectangles to different heights so that we have a 3D building. And so this first extrusion, it's called extrude to point. So he marks a point in the environment that's at the height he wants the building to be. And once that point is marked, then he can select the rectangle, which will automatically be extruded to that height. So this is a way of, again, making a building that's aligned with existing real world features, and in not only in the kind of two-dimensional footprint, but also in its height. And then the second part he extrudes just manually to a given height. Okay, so I hope you kind of see how that works. We ran a study again with this, and what we wanted to see was how the precision of the 3D point marking technique affects the results. And so on the left, you see buildings that were created by users who were using the basic geometric technique to mark points. And on the right, you see buildings created by people using VectorCloud. And so it's kind of interesting, the people using the geometric technique did not do poorly when they were marking the real world points. But as the errors from those points kind of got cascaded and amplified as you used them to create the geometry of the building based on those real world points, you can see that the result is not that good. But with VectorCloud, we get pretty consistent results that an architect might actually be able to use because they're precise. Okay, last thing I'll talk about is, let me just pause this video for a second. We're thinking again about model-free AR when we don't have information about the geometry of the real world, and we want to enable not only single user applications, but also collaborative applications. And so if you're working with someone else and you're both in AR, you want to be aware of what that person is doing, and in this particular case, what they're looking at. So the question is, how do we provide information about your collaborator's gaze direction or gaze target without occlusion, again, in this model-free setting? And so what this video shows is kind of the baseline. So if I just draw a ray going from my collaborator's head position in the direction that he's looking, it's really hard to tell what he's looking at. He's looking at one of these columns over here, but I'm not sure which one it is because without occlusion, I can't tell which column it passes through. So this video just shows that I have to kind of walk all the way to his position in order to be sure of what column he's actually looking at. And I don't want to have to do that. So we tried to come up with some improved cues that mitigate the effect of not having occlusion. And one is that we can use 2 rays instead of 1 ray. And so we asked the collaborator to look at the target, but then also to specify kind of what's the top and bottom of the target. And so in this image, you can see he's pointing at that middle column because the 2 rays go through the top and bottom of the middle column. A second thing we tried to do is to provide better spatial information. And so here's a visualization that we recently came up with. It's called parallel bars. I'll play this video. Sorry, it's got sound as well. The idea is that we provide these virtual bars that extend from me. So you can see I can use my arm to look at, to kind of point in that direction, but that are all parallel to the gaze ray of my collaborator. And this gives me some better spatial information to make up for the fact that I don't have occlusion. And then of course we can combine those together. So here's the double ray with the parallel bars. So we're doing a study on this now. I don't have results from it, but we expect that our improvements will really help people to understand better what their collaborator is pointing at. Okay, so last slide, just some take-home messages from what we've done here. First is, don't rely on human perception for placement of virtual content. It can look correct from one location, but without occlusion and without seeing it from multiple locations, it's really hard to tell if you've got the content in the right place. So these marking techniques based on geometric triangulation that we've shown do a better job of placement. Also, we showed that when you are doing any sort of 3D pointing at a distance with your head or your hand, you need to mitigate the effects of tremor by using techniques like multi-sampling or image-based techniques like the ones I showed. Thirdly, if you're in a model-free setting, which is pretty common, I think, outdoors, you need to provide extra cues to make up for the lack of occlusion, like the double ray or the parallel bar that I showed. And then finally, I guess just some practical take-home messages. I don't want to wait to prototype and evaluate future AR applications, so that I know architects are not going to use HoloLens today to do building design. But I think they might use a similar sort of technology in the near future. And so I want to be able to kind of do research on that now so that there's some lessons learned when those applications need to be built for real. And so to do that, we have to work around current technological limitations. So I've shown you ideas like using simulated AR based on VR technology as one prototyping and evaluation platform. Secondly, like in the building design video, find a large-scale indoor location as a proxy for outdoor use. You can recalibrate user position to known locations, like the white columns that I showed in those videos. And then finally, we found it's really useful when you're doing evaluation to have a second AR display for the evaluator, so that I can see in 3D space, in context, what the user in the study, what the participant is seeing. And that's definitely possible with the HoloLens and with other AR technologies. Okay, so I hope that was helpful and interesting. My contact info is here on the slide, dbowman@vt.edu. And I'm also happy to take questions now if we have time. Thanks.
Thank you, Doug. That was absolutely awesome and very enlightening. So team, I'd like to, if we've got a quick few minutes with Doug, if anybody's got any questions. They're all blown away, Doug, I think.
I don't have a question, but I will echo, this is Don Shin, by the way. Hi there. I will echo that the presentation was fantastic. If we have questions now, great, but another mechanism, especially for the introverts out there that need some time to contemplate what they've just been fed and processing, would it be possible to have questions that come up later at a later point to be shared on Discord so that everyone has access to the answers as well? And Doug, would you be open to participating in that asynchronous conversation?
Yeah, sure. Be happy to do that. I'm not signed on to the Discord server yet, but I can definitely do that.
Okay. Thank you, Doug.